Swayam Prabha. Digital India. Educated India.
Okay, now we have seen that the wave function has this particular form, and we have to determine this normalization constant, which I have denoted by the symbol capital N with a subscript n. So, what is the normalization condition? Well, the normalization condition would imply that if I took psi star multiplied it by psi, then remember I have to multiply it by dx, integrate from minus infinity to plus infinity, and I have to ensure that this is equal to 1. That is the normalization condition. Now, to be very clear regarding the nature of this psi, you see this is the wave function for the nth state, right, that is indicated by the subscript n. So, it is better that I put a subscript n there also. And not only that, as far as my allowed energy levels are concerned, it is best if I put a subscript n to indicate that this n depends upon the quantum number n. So, that means I am going to have an n here as well as there, but when you look at the form of psi, you see we have been writing it in terms of c, everything is in terms of c, and therefore, even this dx I want to express it in terms of dx, right, and that is very easy because here I have the relationship c is equal to alpha times x. So, that means dx must be dx divided by alpha. So, therefore, you will have integral dx divided by alpha. So, let me put a 1 by alpha here, minus infinity to plus infinity psi n star of c, psi n of c equal to 1. This is the condition that I need to satisfy. And in fact, what happens is in this case the wave function does not depend upon, there is no square root of minus 1 occurring inside. So, therefore, this star is irrelevant, star does not affect the function because everything in there is real. So, I can remove the star, and therefore, effectively what it means is that I would have the condition, I would have the thing psi n square sitting there. But then suppose I had taken psi n and multiplied it by psi m and then dx integrated from minus infinity to plus infinity. What would you expect to happen? N and m are not the same. Remember, we discussed the same kind of thing in the case of particle in a box, and we would expect that the two functions are orthogonal, and therefore, this should be equal to 0. This is something that we would expect. We have no proof of that, but this is something that we suspect is valid. So, therefore, you look at this, if you are looking at this expression, what happens is you have e to the power of minus c square by 2, right. Psi n would have e to the power of minus c square by 2, and h n, correct, and this one would have what, I would have e to the power of minus c square by 2 and h m. So, therefore, I want to evaluate the integral from minus infinity to plus infinity of a product which involves e to the power of minus c square by 2 times effectively e to the power of minus c square multiplied by hn multiplied by hm, and I want to integrate it from minus infinity to plus infinity. This is what I want to evaluate, but hn itself, you see, the expression is not very simple, it is somewhat complicated because we have seen the expression today morning. It is there in your notes. Hn may be obtained by this kind of formula, right. Well, maybe I should just write it to remind you how it looks like. So, this is the formula for Hn. So, if I try to evaluate this integral by the usual methods, it is rather difficult, and that is where the generating function is extremely useful. All the integrals that you want in connection with normalization, orthogonality, everything can be evaluated in an extremely simple fashion. And so, let me demonstrate that to you. See, this is my S. This expression is my S. So, suppose I write this generating function once more. This time what I will do is I will not use the variable S, but I will use a different variable which I shall denote as t, and I shall write an expression for S t c. It would naturally be given by e to the power of minus c square plus 2 t c, and this you have to expand as a power series. Earlier the expansion was a power series, involved a power series in S, but now it will involve a power series in T, and what I will do is I will say, okay, I will write t to the power of m divided by m factorial multiplied by HMC, and naturally you see you will have to sum over all possible values of m which will run from 0 to infinity. And you will find that you see these two functions as they are written are extremely useful, and we are going to use it. Now, you look at the integral that I want to evaluate. I want to have an Hn, I want to have an Hm. So, you would realize that if I multiplied these two, I would definitely have Hn and Hm occurring in the product. That is the idea, right. But I want not only Hn and Hm, I also want which one? I want e to the power of, if you look at this integral, there is Hn, there is Hm, these two together is e to the power of minus c square. So, I want that also. So, therefore, what I will do is I will think of this integral e to the power of minus c square into s of small s c, s of t into c, and I will multiply this by dig c, integrate from minus infinity to plus infinity, right. Why do I do that? It is fairly obvious now, because the right hand side will be sigma. The first one may be written as sigma n going from 0 to infinity, s to the power of n by n factorial, and that will be multiplied by Hn of c, right. And then I will have sigma m going from 0 to infinity multiplied by t to the power of m by m factorial and hm of c. All that I have done is I have just substituted the expansions for these two, nothing more, nothing, no manipulations, nothing has been done. All that I am doing is this is defined to be equal to that, while that is defined to be equal to that. So, just multiply the two together and you get this result, and then of course, you will have to put an e to the power of minus c square, right, because you have to have that, and then what will you do? You will multiply by dig c and integrate from minus infinity to plus infinity, but you see none of these things are dependent upon c. So, the integral will actually come here, right. I do have problems with space. Maybe the normalization condition I can shift and write somewhere else. The normalization condition actually says this is the normalization condition. Over this expression I am going to write up here. It is just a double sum with n going from 0 to infinity, m going from 0 to infinity, s to the power of n, t to the power of m divided by n factorial into m factorial and integral dx e to the power of minus c square h n of c h m of c. That is all. And what I am interested in is the value of this integral. I want to know how much it is. In fact, I would like to know when n is equal to m. I would also like to know when n is not equal to m. In fact, I expect that the answer must be 0 when n is not equal to m. Now, you look at the left hand side. The left hand side is this. On the left hand side, you find the variables as c, t and c, but c you have integrated over. So, therefore, the left hand side will depend upon the variables s and t. So, it is a function of s and t, right. And if you look at the right hand side, you see it is a function of s and t, and it is actually represented as a series involving s to the power of n, t to the power of m, with n varying from 0 to infinity, both varying from 0 to infinity. So, suppose I find this function, exactly what this function is, and expand it as a series and looked at the coefficient of s to the power of n and t to the power of m. That coefficient should be equal to the integral that I want to evaluate, correct. I can repeat the argument. If you look at the right hand side, it is a series involving s to the power of n, t to the power of m. The left hand side, if I evaluate it, and then I will find a function, and that function, if I can expand it as a series and find the coefficient of s to the power of n, t to the power of m, that will be equal to the value of the integral that you want to evaluate. So, let us see whether I can evaluate this integral. In fact, what happens is that this integral is easy to perform. Okay, let us see why it is so easy to perform. Let us see that. Let us look at the integral. So, this integral is equal to integral minus infinity to plus infinity dx e to the power of minus c square, as is written here, e to the power of minus s square plus 2sc, and the second function also is written there, that is actually minus t square plus 2 tc. That is all. The integral is just that. I have just substituted for this s and that s, that is all. I have not done anything else. And now, if you look at this, you will find that it is minus infinity to plus infinity dx e to the power of. Interestingly, what happens is that you can write the quantity in the exponent as c minus s minus t the whole square. If you look at this expression, there is a minus c square minus s square minus t square. So, you can write it in this form, but that is not complete. In fact, everything will be fine if you just added a 2st. The way to check that is you expand this and see that the answer is the same, fine. And then you realize that e to the power of 2st is not dependent upon the variable of integration. So, you can take it out. So, e to the power of 2st integral minus infinity to plus infinity dx e to the power of minus c minus s minus t the whole square. That is what it is, the integral. And now you can say, okay, this integral, just make the substitution c minus s minus t is equal to y. C is your variable of integration. I am changing the variable of integration to a new variable which is y. Right. As far as this integral is concerned, s and t are just constants. I am going to integrate over c. So, s and t are kept constants, they are not affected. So, if you have y equal to c minus s minus t, then dy obviously will be equal to dx. So, what will happen to this integral? It is going to be equal to e to the power of 2 st into integral minus infinity to plus infinity dy e to the power of minus y square. That is all, right. And this is a very easy integral in family. I should not say very easy, because it is not a what do I say, it is not very straightforward to evaluate this, but because this is very well known, I tend to say that it is very easy, because this is very well known integral, and the answer is actually square root of pi. So, you get the integral to be e to the power of 2 st into square root of pi. Okay. Any questions on this? Any point which is not clear? So, therefore, what has happened is, this series, you see, I have now evaluated this series. The sum of the series is actually nothing but, this is nothing but how much? Root pi into e to the power of 2 st. Right. This is actually equal to square root of pi into e to the power of 2 st. But e to the power of 2 st, I know how to expand it. Okay. So, what will happen is, I will get root pi into 1 plus 2 st plus 2 s square, sorry, 2 square s square t square divided by 2 factorial plus in general 2 to the power of n s to the power of n t to the power of n divided by n factorial. This is the series, right. So, what do you find? You find that there are only terms which contain the same power of s and t. Right. You do not have a term like s to the power of 1 t to the power of 2, you do not have such a term, right, or you do not have a term of the form s to the power of n t to the power of m with the n and m being different, such a term is not there in this expansion. So, what is the conclusion? The conclusion is that an integral involving n and m different has to be 0, right. So, that is the way we evaluate this integral, and if n is equal to m, what is the value? If n is equal to m, then what will happen is that this actually has the value, if n is equal to m, the coefficient of s to the power of n t to the power of n is how much? See, when n is equal to m, let us say I will have s to the power of n t to the power of n, and you will have 2 to the power of n divided by n factorial multiplied by square root of pi, correct. So, therefore, what happens is that I take the term with the n equal to m here, right. If n is equal to m, the term that is occurring there is s to the power of n t to the power of n divided by n factorial divided by n factorial, because n and m are the same, integral minus infinity to plus infinity dx e to the power of minus c square Hn of C Hm of C is equal to what? You will have the square root of pi which was sitting there, two to the power of n divided by n factorial, with of course I mean I should say s to the power of n t to the power of n, because I have put s to the power of n here and t to the power of n there. So, this is what is going to happen, and obviously that means, well, I have made a slight mistake, it is not m, but I have put m equal to n. So, there is an n here. So, you can actually remove s to the power of n t to the power of n, and so what do you find? You find the answer that you wanted, minus infinity to plus infinity dx e to the power of minus c square hn c square is equal to how much? There is 1 by n factorial 2 times here. So, therefore, you will actually get the answer root pi 2 to the power of n. This 1 by n factorial square actually can be taken to the other side, and you will get an n factorial. So, this is the answer, and the answer is very general, it is valid for any n, and that is why I said the generative function technique is a very nice technique, because I did not have to look at a particular value for n, I got the answer for all possible n in one shot. Okay. Not only that, I also found that the functions are all orthogonal, they are all orthogonal to one another, which is another nice thing. I got all these results out of the generating function. So, finally, what is the normalization factor? Well, where is my normalization condition? The normalization condition is here, right, and the way it is written is this. So, let us rewrite this, I mean write this once more, 1 by alpha integral minus infinity to plus infinity, psi n is given by that expression, okay, psi n is given by this expression. So, therefore, I will put n square e to the power of minus c square hn square c is equal to 1. This is the normalization condition. And so, I can take this n square out, n square by alpha integral minus infinity to plus infinity e to the power of minus c square hn c square dx is equal to 1. It is a dx missing in this expression, I better write this. But we have just now evaluated this part, and that is written here. So, therefore, n square by alpha times root pi 2 to the power of n factorial is equal to 1. For n itself, is equal to alpha by root pi 2 to the power of n factorial to the power of half. That is the normalization factor. And so, finally, what is the wave function for the nth state? the wave function for the nth state psi n is equal to that nn e to the power of minus c square by 2 h n of c, and n is equal to alpha divided by root pi 2 to the power of n factorial to the power of half. And just to remind you, c is equal to alpha x, alpha is equal to m k divided by h cross square to the power of 1 by 4. Right, we have completely solved the Schrodinger equation for the harmonic oscillator. Everything that we wanted is here now. And then we look at, I mean, it's not just enough to solve the equation, we have to look at the different possible levels of the system. Let us look at that. Well, I don't need these things anymore, so this is the potential energy of the harmonic oscillator. Let us look at the situation where n is equal to 0. What will happen? The energy will have the lowest value, because energy is of the form E n is equal to n plus half h nu. N can take on the values 0, 1, 2, 3, 4, etc. So, n equal to 0 is the lowest possible state. We always say that is the ground state of the system. So, the energy will be E 0 and it will be equal to half h nu. Now, notice that the energy, lowest possible state's energy is not 0. So, the system has what we refer to as a 0 point energy. As I said, in the case of the particle in a one dimensional box, this is nothing but a consequence of the uncertainty principle, because the particle simply cannot be sitting at rest. Okay, it is not possible, because that will violate the uncertainty principle. So, it has to move, and if it moves, it has kinetic energy, okay, and therefore, the energy cannot be 0. So, that will be the state. Let me represent that in the figure. Here the energy is 0, but that is not possible. The first allowed energy level has n equal to 0, and I can probably represent it by this line. The energy is half h nu. The next allowed energy level obviously will be equal to 3 by 2 h nu, and I can represent it by this line. So, 3 by 2 h nu, then the next is of course 5 by 2 h nu, then 7 by 2 h nu, and so on. Now, you should also notice that the spacing between these two successive energy levels, see, if you look at these two energy levels, the spacing is actually h nu, and it is the same for the next two energy levels, and it is the same for the next two energy levels. So, therefore, you get a series of equally spaced energy levels. This is a speciality of harmonic oscillators. If you remember, in the particle in a box, what happened? You had energy levels, but the spacing between them were increasing as you went up. Here the spacing is actually the same. Okay. So, when n is equal to 1, as I told you, the energy is 3 by 2 h nu, n is equal to 2, 5 by 2, then 7 by 2, and so on. Let us look at the wave function for the ground state. What would be the wave function? The wave function would be psi 0, which will be given by n0. What I am doing is I am using the expression. Where is my expression? Yeah, here it is. n0 e to the power of minus c square by 2 h0 of c. Correct? This is my expression. And you can actually evaluate n0. Where is the expression for n0? Well, this is the expression that I have derived. So, you just have to put n small n equal to 0, then what will happen? You will get alpha divided by root pi, 2 to the power of 0 is unity, 0 factorial also by definition it is unity. So, therefore, you get this to the power of half e to the power of minus c square by 2, and h0 we did evaluate it in the morning, it is equal to 1. So, therefore, the wave function is this, and if you want you can express it in terms of x. So, how will you do that? You will replace the c here with alpha x, but why should we do that? I mean, instead of using x we can just use c, it is proportional to the position. So, therefore, what we can do is okay, we can say okay, this is c is my horizontal axis instead of alpha, because one is proportional to the other. And then suppose you make a plot of this function against x or equivalently against c, what is the answer that you are going to get? It is what is referred to as a Gaussian function, e to the power of minus c square by 2, it is a Gaussian function. So, if you make a plot of such a Gaussian function, what happens? When the value of c is equal to 0, it has the largest value, and as you increase the value of c in the positive direction, the function will decrease, or if you decrease the value of c in the negative direction, again c square will increase and therefore, the function will decrease. Okay. So, therefore, what happens is you will get a curve which looks like this. So, that is the ground state of the system, and it is also obvious to you that this is what we refer to as a symmetric state. If you replaced c with the minus c, you look at this expression, if you replaced c with minus c, the function remains unchanged, and that is reflected in the plot that I have made. That is the ground state. So, the ground state wave function is actually symmetric with respect to the replacement of c by minus c, and it does not have any nodes, you can see that also. What about the next one, psi 1? It is n1 e to the power of minus c square by 2 h1 of c, and that is equal to alpha. Where is my general expression? Here is my general expression, alpha by root pi 2 into 1 factorial, 1 factorial actually is 1, to the power of half e to the power of minus c square by 2 into h1. h1, if you look into your notes, you will find that it is 2c. So, therefore, the interesting part is this e to the power of minus c square by 2, which actually says that the function will be 0, becoming 0 at infinite distance from the equilibrium position, right. E to the power of minus c square will ensure that the function is well behaved, but in addition to that you have this c. So, if you have the c, what will happen at the origin where c is equal to 0, this function will vanish. And not only that, you can see that if I replaced c with minus c, the sign of the function will change, and therefore, this is an antisymmetric function. So, how will it look like? I will make a plot. I hope this is not too confusing, because I am plotting different functions in the same picture. If you find it confusing, I will draw it separately. So, that is our psi 1. this lower one was psi 0. Then I will do one more, psi 2 would be equal to alpha by root pi 2 square into 2 factorial, which is 2. So, effectively you have 8 there. So, this is the function. Remember H2 I had written in the morning, it is actually 4 c square minus 2. So, again you will notice that this is an even function first of all. The second thing is where are the zeros of this function? Well, when you have 4 c square minus 2 is equal to 0, when this is equal to 0 you would have it equal to function equal to 0. So, when does that happen? That happens when c square is equal to 1 by 2 or c is equal to plus or minus 1 by root 2. There are two nodes. This is something that we would have expected. So, how will the function look like? Well, these are the two nodes. The nodes are actually symmetrically located. These are the two nodes, and the function would look like that. It is symmetric. I mean, the way I have drawn it, it may not appear completely symmetric, but it is symmetric. And with that knowledge, actually we can now go and draw the next one. I will not try to write the expression. The next one would have 3 nodes, so it is more difficult to draw. So, that will be the appearance of the next one, and similarly you can go on plotting the other ones if you like. As the value of n increases, what happens? You have more and more nodes. In fact, the nth function would have n minus 1 nodes. Let us again go back to the ground state, this one. Okay. What is the wave function? Well, I will think only of the ground state now. This is the wave function, and as I have told you, it is a symmetric function in x. So, suppose I imagine that I make a series of measurements of the position of the particle and take its average. Okay. I can actually get that average by calculating the expectation value of x, and what will that be for this particular problem? I am going to calculate it, but is it necessary to calculate it is the question. See, you have the equilibrium position, which is x is equal to 0, and then you have the wave function which is symmetric about the equilibrium position. So, when you make a measurement, it is equally likely that the particle will be found on this side or on the other side. If it is found on this side, its position coordinate is positive, while on the other side the position coordinate will be negative, and therefore, on an average the expectation value of x you would expect is 0, right. That you can easily verify. It is a fairly simple thing. How will you do that? Well, I do not think I need to do the integral, because I can say that you look at the integrand. Integrand is from minus infinity to plus infinity, but the integrand is an odd function of x, correct. It is an odd function of x, and if I integrated an odd function from minus infinity to plus infinity, what has to be the answer? There will be a contribution from the negative x region, and that will be cancelled by the exactly by the contribution from the positive x region, and therefore the answer has to be 0. Similarly, if I thought of Px, average value of Px, what would you expect? See that it is in the ground state, okay, and the particle, if you are measuring the momentum, maybe sometimes it will be moving in this direction, but it is not going to go away, it will come back. So, it will go back in the reverse direction sometimes. So, therefore, average value of momentum you would expect is 0. What is more interesting is actually to calculate expectation value of x square. I will not actually evaluate it, but I will tell you how to evaluate it, and then maybe you can do it as an exercise perhaps, if you like. What is the definition of x square? Let me say I am thinking of the nth state. That is what I have written here actually. Even though I said I am going to speak about the 0 state, the expectation value that I wrote is general. The answer is valid for any general n. So, let us say I have psi n, x square psi n. It is, I am not going to put the star here, because the function is real and therefore star has no effect. So, I want to evaluate this integral, that is the expectation value of x, right. And here you have things written in terms of x, you will have to change over to your c, that is better. So, therefore, how will you do that? You have x defined as c by alpha. So, what will happen is you will have integral psi n square c square by alpha square into dc divided by alpha, right. You are changing x square as well as dx into expressions in terms of c and dc. So, therefore, what happens is you will get 1 by alpha cube integral psi n square c square dc from minus infinity to plus infinity. And this is actually equal to 1 by alpha cube minus infinity to plus infinity. Let me substitute for psi n square. It is actually e to the power of minus c square h n c square, right. This is just psi n square. There must be a normalization factor which you will write as n square, right. Normalization factor has to be there, then you will get this, and this is multiplied by c square, okay. That is the integral that you will have to evaluate, fine. Now, this is almost the normalization integral if it were not for the factor of c square and this alpha cube. This c square is there. So, you have a different integral, not the normalization integral, but you have this integral. So, the question is how will you evaluate this? For that we can make use of one of the identities that I had derived earlier. The identity that I can use is to be taken from the book. I had shown this in the morning. It says that h n plus 1 minus 2 c h n plus 2 n h n minus 1 is equal to 0, right. This is an identity that we had derived in the morning. So, therefore, I can rewrite this and say this means that C times Hn is equal to how much? Hn plus 1 plus 2n Hn minus 1 divided by how much? 2. Okay. So, C times Hn I can write like this, and therefore, if you multiply this by C square Hn will be C Hn plus 1 plus 2n C Hn minus 1 divided by 2, fine. And then for each one of these, if C into Hn plus 1, I can again make use of this identity, and for that also I can make use of the same kind of identity. So, it is a little bit lengthy algebra which I am not going to do, but if you did it that way, ultimately what will happen, your C square will disappear, the C square will disappear, and you will have things written in terms of the Hermite polynomials alone, and then you can use the orthogonality theorem and get the answer. This is how the calculation will proceed. If you wanted to calculate the expectation value of x square, but I can tell you what the answer will be. I think I have spent enough time on the harmonic oscillator, so therefore I am not going to evaluate this, but the answer is actually the following. In fact, the answer can be written in this form: half k x square average is equal to n plus half h nu divided by 2. That is the way in which you can write this. You see, I mean, this is not very surprising, because n plus half h nu is the total energy of the system, half k x square is the potential energy, average value of potential energy. So, this says that the average value of the potential energy is equal to half the total energy, which is not surprising, because the system has both kinetic and potential energies, and for this system it is such that the average value of potential energy is equal to the average value of potential energy is equal to the half the total energy. That is all that happens, and you will get this result if you evaluated these integrals. Okay. Okay, I think I will stop my discussion of the harmonic oscillator at this point, and then start a discussion of the hydrogen atom in my next lecture. Thank you for listening.